So in this video, we're going to have a look at a type of titration question that will involve identifying a metal in a compound. This could be given to you as a practical, or it also could be given to you just as a calculation in your theory exam. So what you'll start off with is a metal oxide or a metal hydroxide. That will be your base, and that will be titrated against a standard solution of an acid. In other words, a solution of acid that you know the concentration of, so that will go into the burette. You will be told the general formula of the metal oxide or the metal hydroxide, and from that you'll be able to tell whether it's a group 1 or a group 2 metal. It's more than likely going to be a group 1 or group 2 metal, although it could be a different metal. So if it was a group 1 metal and say it was a metal oxide, you would have your metal, let's give it the formula M, just as the general formula of our metal. And if it's in group 1, it's going to have a valency of 1. If it's the oxide, that's just going to be with oxygen, which would have a valency of 2. Swap and drop that and you get M2O would be your general formula of a group 1 metal oxide. But if it was a metal hydroxide, you would have your metal, again with a valency of 1. Hydroxide is OH minus, so it would be OH with a valency of 1. Swap and drop that, you would get a general formula of MOH. So if you had either one of those two general formulas, you would be able to tell that your metal was from group 1 or it has a valency of 1. If it was group 2 then, your metal is going to have a valency of 2. So in terms of the metal oxide, your metal and your oxygen has a valency of 2. So those cancel out to give 1 to 1. So your formula would just be MO. So that would be a group 2 metal oxide. And then with the hydroxide, your metal has a valency of 2. Your hydroxide ion has a valency of 1. So if you were to swap and drop that, you would get M. Then you need to put your OH in brackets to show that that little 2 that you're swapping down applies to the whole hydroxide ion. So that would be M brackets OH brackets 2. So from your general formula, try and work out at the start, is it likely to be a group 1 or a group 2 metal? Because that means with your final answer, you'll be able to check and see, does that make sense? So with these questions, you'll normally start with a solid metal oxide or metal hydroxide that will then be made up into a solution. So it involves a dilution to some extent, but just essentially making up a standard solution. So you'll need to factor that into your calculations as well. So you'll be given the mass of the compound to start with, and that will, the calculation will allow you to calculate the number of moles of the metal oxide or hydroxide from the titration. You can then use the equation once you've been given the mass, once you've worked out the moles, then you can calculate the RFM using the equation RFM equals mass over N. And that's just a rearrangement of your N equals mass over RFM, or mass equals N times by RFM. So that will give you the RFM of the metal oxide or the metal hydroxide. And then what you can do is you can take away the relative atomic mass of your oxygen and or your hydrogen to work out the relative atomic mass of your metal. Let me give you an example of that. So say, for example, you were working with a group 1 metal hydroxide. The general formula of your metal hydroxide would be MOH. And the RFM of that is the total of the relative atomic mass of your metal plus 1 oxygen atom plus 1 hydrogen atom. What we want to work out is just the relative atomic mass of the metal. So that's fairly easily done. All we need to do is, if we have the RFM of your metal hydroxide, and I just want M, I can simply take away the oxygen and take away the hydrogen from the total RFM, and that will give me the relative atomic mass of M. And we'll see that in the examples that we do. Just to take you through one more example, if you had a group 2 metal hydroxide, it's a little bit more complicated, but just think about what atoms you have in the formula. So the total RFM is your metal, plus this time you've got 2 oxygen, so it would be 2 times O, and the relative atomic mass of oxygen is 16, but just to keep it general at this stage. And you've also got 2 times your hydrogen. So when you're working out your relative atomic mass of M, your unknown metal, what you're doing this time is you're getting your total RFM and you're taking away 2 times by oxygen, so that'll be 2 times 16, which is 32, and you take away 2 hydrogens, which is 2 times 1, which is 2. Okay, so just think about what your formula is when you're working out your final part of the question, which will be the relative atomic mass of your metal. And from that, you will be able to identify what the metal is just by looking at your periodic table and seeing what element does that match up with. So let's have a look at the worked example on page 37. And one thing I need you to do before we start is actually change the starting mass of this compound. I had a go at this calculation and the final mass didn't work out as anything that makes sense. So if you could change that to 1.57 grams. So 1.57 grams of your unknown metal hydroxide. That just then gives us an answer that makes sense. So the unknown metal hydroxide has the general formula MOH. So looking at that formula, have a little think, which group do you think your metal is likely to be from? Well, we know that it has a valency of 1, so it's likely to be a group 1 metal. Okay, obviously it could be a transition metal with a valency of 1, but it's likely to be a group 1 metal. So we start with 1.57 grams of our solid metal hydroxide and we dissolve it in water to make a solution of it, and it's placed in a 100 centimetres cubed volumetric flask and the volume made up to 100 centimetres cubed. So we know that we have 1.57 grams in 100 centimetres cubed of a solution. What we then do is we take a 25 centimetres cube sample of this solution and put it into your conical flask. That's what you're going to use for then your titration. That is titrated against 0.5 molar HCl using phenolphthalein indicator. The average titer was found to be 14 centimetres cubed. That is your HCl. And then you're given the equation for the titration reaction. So what I'm going to do below is just a really quick wee diagram just to summarise this method. I personally find it helpful when doing these titration calculations to make sure I've worked out, okay, well, what fraction of my moles am I taking across in this sample or this sample, or what ratio is there in the titration. You could try and fit it in this space here or somewhere else where you can find room, or you can just watch along for now. But I think sometimes these type of diagrams are helpful when you're doing the calculations. So you're starting with 1.57 grams of your metal hydroxide, and in reality what you'll do is you'll make up a small volume of that solution. You'll maybe dissolve it in anywhere between 10 to 50 centimetres cubed of water, and then that will be all placed in your volumetric flask. So you're transferring all of that into your volumetric flask. So that will be your standard metal hydroxide solution, MOH solution, and that is made up to 100 centimetres cubed. What we're then told is that once that's made up to 100 centimetres cubed, we're taking out 25 centimetres cubed of it. So we're taking out 25 centimetres cubed of our 100 centimetres cubed standard solution, and we're placing it in the conical flask for the titration. So we've taken 25 out of 100. So really what we've got here is a quarter of the metal hydroxide solution. So it's going to be a quarter of the moles essentially that we're taking out of the solution, and we'll come back to that idea in a second. And what we then want to do is take that solution in the conical flask, sorry for my terrible diagrams, and we want to titrate that against our standard hydrochloric acid. So again, in the conical flask we just have a quarter of our overall metal hydroxide solution, and in here we have 0.5 molar HCl. We also know from our question that our titer is 14 centimetres cubed, so that you could add that to your diagram as well. So what we want to think now about is the number of moles. So what we are going to work out is the number, what we're going to work out first of all is the number of moles of HCl. That is titrated against your metal hydroxide, and you can see from your equation, I'll maybe not write the whole thing, but you can see from your balance symbol equation that the ratio is 1 to 1. So what I'm going to be doing in my calculation is bringing the number of moles of hydrochloric acid over to my metal hydroxide, and that gives me a 1 to 1 ratio. So once I've worked out the number of moles of HCl, the number of moles in my conical flask is exactly the same. So essentially what I'm doing, because of my ratio, is I'm timesing the number of moles by 1. Essentially it's the same. So if you wanted to write there, that's because you have a 1 to 1 ratio. Then what I'll be doing is working backwards and calculating how many moles of my metal hydroxide do I have in my volumetric flask. Remember that in the conical flask we only have a quarter of the moles because we only took 25 centimetres cubed out of your 100 centimetres cubed. So to work out how many moles you have in your volumetric flask, what you're doing is you're timesing by 4. Again, sorry, that's a wee bit cramped and messy. So in other words, there's 4 times as many moles of metal hydroxide in your volumetric flask as there are in the conical flask. Then you'll essentially be asked how many moles are there in the original sample in the 1.57 grams. Well, that's just the same number of moles as well. In other words, we're timesing by 1. Why is that? Well, it's because I transferred all of my 1.57 grams. I made up a solution of it and put it all in the volumetric flask. So essentially, once we've started here at our number of moles of hydrochloric acid, it's a 1 to 1 ratio. So it's the same number of moles in the conical flask. It's 4 times as many moles of our metal hydroxide in the volumetric flask, and that's the same as the number of moles in my 1.57 grams. And that's at the point then when you can use your RFM equals mass over N. Now you don't need to remember all that. Your calculations are structured. They are broken up into different steps. And so you can just follow along with those steps, those broken up questions. But I think sometimes it's helpful to have an overall picture of the titration and the dilution making up your solution so that you can understand the number of moles at each stage. So taking that diagram away, let's have a look at our questions. So it says, determine the identity of the metal M using the following headings. So first of all, the number of moles of HCl used in the titration. So remember, all titration calculations start with your average titer of the thing that's in the burette. So number of moles is N equals CV. So your concentration of your hydrochloric acid is 0.5. The volume is your average titer, but remember we need to convert that into decimeters cubed. So you divide by 1,000 and that gives you 0.014 decimeters cubed. So it's 0.5 times 0.014. And that should give you, if you put that into your calculator, try and do it along with me, and you can even write your answers in afterwards, is 7 times 10 to the minus 3 moles of HCl. Next question is number of moles of MOH present in the conical flask. Again, look at your diagram. This is essentially your titration reaction. So remember that, and your equation is given to you up here. Your metal hydroxide is reacting with your HCl in a 1 to 1 ratio. Don't need the right-hand side of the equation, but obviously you do need to write the full equation to make sure that it's balanced. But we know that we have 7 times 10 to the minus 3 moles of HCl. Bring that over to your metal hydroxide in a 1 to 1 ratio. So that means that I have 7 times 10 to the minus 3 moles, and that's in your conical flask. So that's in your 25 centimetres cubed sample in your conical flask, if you wanted to write that down. So I know that I have 7 times 10 to the minus 3 moles of metal hydroxide in the 25 centimetre cubed sample that I took from my volumetric flask. The next question asks for the number of moles of metal hydroxide present in the 100 centimetres cubed in the volumetric flask. Really what we're doing here is just multiplying by 4. Just look back at your diagram and look at moving backwards in terms of our moles, going from the conical flask to volumetric flask. We're going really from 25 centimetres cubed to 100 centimetres cubed. We know that we have 7 times 10 to the minus 3 moles in your 25 centimetres cubed. So to get the number of moles in your 100 centimetres cubed, you times by 4, and that should give you 0.028 moles. And that's in your 100 centimetres cubed volumetric flask. Part D then asks for the number of moles of metal hydroxide in the original sample. Well, at this stage you need to remember and look back at your diagram that you transferred all of your 1.57 grams of your solid original sample into the volumetric flask. So that's just the same as the previous question. So if all of our metal hydroxide was transferred into the volumetric flask, then the number of moles in the original sample is the same as the number of moles in the volumetric flask. So essentially I'm just timesing by 1, it's the same answer, so it's 0.028 moles. Next question asks you to work out the RFM of your metal hydroxide. At this point we're using the equation RFM equals mass over N. What the mass is your mass of your original sample, which is 1.57. And remember, we changed that mass at the start of the question. The number of moles is 0.028. If you put that into your calculator, you should get 56.07. So that gives you the RFM of the overall metal hydroxide, but what we're interested in is just the relative atomic mass of the metal, and therefore we can work out from that the identity of our metal. So remember that the RFM we've just worked out is essentially M plus O plus H. So if I want to work out what M is, I need to take my RFM, which is 56.07. I need to take away my mass of oxygen, which is 16. And then I need to take away the mass of hydrogen, which is 1. And that should leave me with just the mass of the metal. So 56.07 minus 16 minus 1 should give you 39.07. And that is roughly 39. The relative atomic masses on your periodic table are just generally whole numbers apart from chlorine, and so you can round that off to 39 to try and help you find the identity of that. So what you do now is you look at your periodic table and you see if there is a metal that has a relative atomic mass of 39. And remember, you can kind of narrow down your search by thinking, well, we worked out this is probably going to be a group 1 metal. So if you look down your group 1, you should see that potassium has a relative atomic mass of 39. Remember, you're looking at the atomic mass and not the atomic number. So if the relative atomic mass of potassium is 39, then your metal is potassium. So hopefully those calculations make sense. Again, they involve a bit of a dilution, making up a standard solution, and then your titration calculation, and also then applying that to then working out the relative atomic mass of an unknown metal. If you're not sure, if you want to go over that again, please replay the video and see if that helps, or if there's anything you want to ask, please do get in touch. But what I'd like you to do now, there's just 2 questions in exercise 7. I'd like you to give them a go. So if you look at question 1 here, just note that should be a little subscript 2. I've checked these calculations and they do work okay, so all the values are correct. Just be careful with this one. Your formula is obviously M brackets OH2, so when you're doing your final step of working out your relative atomic mass of your metal, remember that you've got 2 oxygens and 2 hydrogens in your total formula. And then question 2 is a group 1 metal hydroxide, so very similar to what we've just done. So give those a go, and again, please do get in touch if you're getting an answer that doesn't make sense, doesn't match up with any metal on the periodic table, and see how you get on.